This is Knowledge Engineering with Semantic Web Technologies. And these are the extra parts of lecture number 4 for OWL, Rules and Reasoning. Today we want to deepen our knowledge in RDFS semantics. And as you already know from the first part of the lecture, the semantics for RDFS will be introduced via a stepwise interpretation. And we start with a simple interpretation here. So if you just try to remember, to give a model theoretic semantics for RDFS, first we have to, of course, map RDFS to a logic, which then has to be mapped to a more simpler model in set theory. So first we have to consider what are the statements in RDFS to treat RDFS like a logic. And the statements we will see are all the triples, so we have already seen that. So each subject, predicate and object is a statement, but also then a summary of statements in an RDFS graph is a statement. So these are all the statements we are looking at. And then, of course, for a logic, we also have to define an entailment relation. And therefore, we define a set of interpretations. And this now will be part of the subsequent lecture parts. We define a set of interpretations and denote which of these are a model of a given graph. So we start right now with the so-called simple interpretation, which takes care of the interpretation of triples and RDF graphs. And then we will go forward and look at RDF vocabulary and RDFS vocabulary and the interpretation of that one. So our goal is a formally correct mapping of the intention which is behind RDFS and which has been first described in natural language. So let's start with a simple interpretation. So what we have to do first is, of course, we have to look at the RDFS vocabulary and our simple interpretation I we have here. And we want to map it to sets. So we have to define sets we are dealing with. So the first set we are looking at is IR, which is a set of which is non-empty, and it's the set of all the resources. So our domain of discourse of our interpretation I. And apart from the resources, we have special resources. We'll see that later on. This is a set of all the properties of I. This is IP. Then for the properties, I need a kind of extension functions, which maps a subject with a property to an object. So this is a function assigning each property to a set of pairs from the resources we have here. You see this denoted here. And this IX is also called the extension of a property. So besides the extension function for properties, we also need a mapping function which maps URIs from our vocabulary V to the union of resources and properties. So this is the other mapping function we need for our URIs. Then, of course, besides URIs, we also have to take care about literals. So here we have a function which maps usually typed literals of V into the set of resources, because we treat typed literals as kind of resources. And then in the end, we also have a set, also among all the resources we consider, which is a set of literals. And this at least contains all untyped literals of V. So these are the basic blocks, the basic building blocks we are dealing with. Okay, let's go further. What we do now is we define a simple interpretation function for the mapping of all literals and URIs from our vocabulary V to the resources IR and the properties IP. But we have to do this, of course, in a formally correct way. So therefore, we also have to take care about what is done with the literals. So what does this function do with literals? So for every untyped literal A, this is mapped to an element A, which is somewhere in IR. So you see this, first we are treating an interpretation of untyped literals. Then if this untyped literal should have a language tag, for example, this occurs of course in RDF, then this is mapped to a pair, which is also then part of IR. So what then with a typed literal? Okay, a typed literal that will be mapped to our mapping function IL that we have already treated with. And this, of course, then maps it to the set of all the resources. And then, of course, every URI is mapped to IS. So this mapping function which maps URI to, again, the set of resources. So what you see here, our interpretation function that we have here consists of a bunch of mapping functions that maps, of course, the parts that we have in a triple to these sets we have just defined. So if you try to visualize this here, you see it quite clearly what happens. You see here the URIs are mapped via your mapping function IS to the resources and properties. The type literals are mapped also to the resources via the mapping function IL. You see that the properties, they have a property extension function, which then maps to always resources with each other with one property, and then also you can see that the untyped literals here are mapped to the set LV of all literal values that are available. So this is the basics of our, or the fundament of our simple mapping. Looks quite nice, doesn't it? So now the question is, so when is this interpretation really also a model of a graph? So you see here a small example. We have here Pluto again. We had this in the first examples with RDF. So Pluto has been discovered in 1930, and it has been discovered by Clyde Tombaugh, who is the discoverer of Pluto. So when is this class or our interpretation a model of a graph? Okay, for that we have somehow to decompose the graph and say if the interpretation is a model of all of the triples that are in the graph, then of course we can do the deduction that then also the interpretation of the graph is a model of the graph. Okay, but for this we have to give an interpretation for a triple. So this is the basic building block. So let's consider a triple. When is the interpretation, our interpretation, a model of a triple? When is it true, when is it false? So the condition is really, really simple, so therefore the name simple interpretation. So what you consider here, you have subject, property, and object, which comes from your vocabulary. And then you say, if the interpretation of your subject and the interpretation of your object are part of the extension of the property by which they are connected in the triple, then the interpretation of that triple is true. So this is always true. So this holds for all so-called grounded triples. Grounded triples do not contain blank nodes. You see here, blank nodes we have just for simplicity left out, but we will soon talk about blank nodes too. So this is the condition. Then, of course, this triple or the interpretation of this triple is true, so it's a model of the triple. So this means the interpretation I assigns a truth value then also to a graph G, which consists of many triples, and the interpretation of a graph is true if the interpretation of all triples in G, of course, is true. And in this way, we can do a simple interpretation of the basics, building blocks of RDF, which is a triple graph. Up to now, we have nothing said about what is the semantics behind the vocabulary that we use. But we have also, of course, to define what can be done with the help of triples or simple triples. Okay, yeah, triples, but we said we did not take care about blank nodes. So what about blank nodes? For the blank nodes, we need a separate mapping function. So let A be a function assigning all blank nodes to elements of IR. So of course, we want to treat blank nodes like the resources we have. But of course, we have to map them there because they are not originally in there. So then, for our interpretation I define a new interpretation, I plus A, be defined as A, where in addition for all B nodes, then it holds that, of course, the interpretation of a B node then will be carried out with, of course, the mapping function A that assigns the B node to an element in IR. So this is an additional mapping function that I introduce simply for the B nodes. So, and then of course an interpretation I is a model of an RDF graph G if there exists an A such as all triples of G with respect to our combined interpretation function I and A are true. So this is a simple extension. So for the blank nodes I need, as you see here, a new mapping function. The overall conclusion is then, so if I want to express the entailment function that is really needed, so a graph G sub 1 simply entails another graph G sub 2 if and only if every simple interpretation that is a model of G1 is also a model of G2. And there we have the entailment relation between two graphs, between statements. So this is all we need. And we have defined the entire semantics. So let's have a look at an example. So what I have done here is I have introduced a blank node right into the node, into the graph that we have seen before. So we have dbpedia Pluto, and I have defined that this Pluto is connected with another blank node, which is connected via the property that it is a discovery. And the discovery has a discovery point in time, so this is then connected by the property discovered, and it has a discoverer. And of course, Pluto has been discovered in 1930, and it has been discovered by Clyde Tombaugh. Okay, so far for our graph. Let's have a look at the interpretation. First thing I have to do is, of course, I have to define the mappings of all our resources to of all our triple resources to the set of all the resources. And the set of all the resources IR here, for example, I have denoted with these Greek letters. So for example, in IS, which is the mapping functions from URIs to our resources, I map Pluto to Xi, I map Clyde Tombaugh to New, I map Discovery to Tau, and so on and so on. So you see, I have here first mapped all the available URIs to elements of IR. So I define IR right over there. You see IR consists of all of these elements. Then IL, so the mapping function for literals is empty simply because we have an untyped literal here, and this will usually first not map with a special function of typed literals to the set of resources. And then, of course, I also have to define this additional mapping function for blank nodes, which is A, and I say, okay, I map A simply also this node which has the reference ID 1, I map this blank node to another element of IR. So what you see then here is, of course, on the right side, you have the sets IR with all the resources. You have the set IP, which contains all the three properties we have, and we have the set LV, which is the untyped literal value. But all of them, of course, are resources, therefore they are also all in IR. And then I define the extension function for all of my properties. So, and you see here, I simply substitute the URIs with the elements of IR and IP. So you see that here. Okay. Now then, of course, when I choose exactly this mapping for my vocabulary, for my URIs that I have, and I choose the mapping A for the blank node in the way I suggested it, then of course I can simply write or explicitly state, denote, represent also what is the outcome of the extension of the properties I have here. And if the extensions really confirm then to subject and object from the triples, I'm done and the interpretation is true. And as you see here, exactly this holds because Pluto here is connected to the blank node via this discovery property which has been mapped to Tau. And for example, the blank node then is connected to Clyde Tombaugh, and the blank node is connected to 1930 with all these interpretations at hand. And you see exactly now, of course, the interpretation then can be seen as a model for all of these triple, and then it can be deduced that also the full graph will become true, and our interpretation that we have explicitly stated here then is also a model of the graph. Of course, only with respect to simple interpretation, because we do not take care about the meaning of the vocabulary. Okay, so this is the first part of RDFS semantics, which maps simply triples and graphs to a simple interpretation. So for the next part of the lecture, also an extra part, we will have a look at the interpretation of RDF and RDFS vocabulary.